All right, so the first thing you're going to write is show that show that square root of 5 is irrational. Write that down. Show the square root of 5 is irrational. All right, now there are two proofs that two possible methods you could use result in the same thing. We show that both of them are irrational. Let me show you this one first. All right, before we go any further, what is a rational number? Because it's either irrational or rational. What is a rational number?
And a number that can be expressed as a over b, where b is not a, but b is not 0.
All right, you're partly right. So you mentioned the a over b and b is not 0. But what about a and b? What kind of numbers are they?
Real numbers.
Well, real, yes, but be more specific. Because this is a
Natural.
Integer.
Integers, correct. So a and b are integers. Some people you can also use whole numbers, but because square root can be negative, well, you know what? Integers, yes, that's the best one to use. So, as Anthony said, can be expressed as a over b, and a over b have to be integers, and b can be 0. You mentioned all that. Good. Now, for this proof that I'm going to show you, we're going to specify it a little bit more because we're going to prove by contradiction. You know, when you prove something by contradiction, it means that one of the assumptions that you made, if you made any, is not true. It must have been the other way around. You guys saw that in, wait, I don't know if Akila did that. My friend, did color geometry? My friend.
Sir, repeat.
Did both of you do college geometry?
Yes, sir. College geometry? I did it.
Okay, I know Anthony did it, so. So you know what contradiction and proof by contradiction is. All right, so let's get started. We're proving that the square root of 5 is irrational. So first we assume, oh boy, I need to say stuff more than write it because my writing is bad. Assume that the square root of 5 is rational. This is how we're proving it. Assume the square root of 5 is rational. All right. So this would then mean that we can express the square root of 5 as some, since he said a over b, let's use a over b, as some fraction where a and b are integers. Of course, the b could be 1, a could be 1. It could just be a simple integer in the end. So it doesn't have to be a fraction itself. But b can't be 0. All right. So we're going to say that this a over b is in its simplest form. And by that I mean that they have no factors in common apart from 1. So they have no factors in common. So it can't be reduced any further. Right, so once we have that set, then we can continue the proof. So a and b are both integers, and a over b is in its simplest form. I'm reducing it further. So like 2 over 3, or there's nothing like 8 over 12. Has to be simplest integer or simplest integer. Can't go any further with reduction. So next step, we're going to square both sides. So that will give us 5 squared. Square root of 5 squared, which is 5, is equal to a squared over b squared. Oops, b squared. So we can just cross multiply to give 5b squared is equal to a squared. So remember, as I said before, there are 2 ways you can go about it. I'm going to do it this way first. So if b is an even number, right? If b is even, then that would mean that if b is an even number, then what does that say about a? All right, let me go a little further. If b is even, then what can we say about 5b squared? It must be what? Even or odd?
Even, sir.
Even. What is wrong with my b? Oh Lord, the more I try to fix the worse it gets. So if b is even, 5b squared is even as well. Because b squared is going to be even, and then 5 times that is still even. So it's even. Which means what about a squared?
It's even as well.
Alright, it means that a squared is even as well. Because if a squared is equal to an even number, then a squared must be even. And what would that mean about a over b? Alright, before we go any further, it means that if b is even, it would mean that I had multiplied a 2 by itself. Because, like, for example, 6 is even means that, remember, when 6 is 2 times 3, when you square the 6, 2 times 3, you're getting 2 times 2, 3 times 3. So for a number to be even, for the square of a number to be even, it must have meant that the original number was even as well. You follow what I'm saying? So if I tell that the square of x squared is even, it means that x must have been even. Why? Because the only way you can get an even number is if you had multiplied it by 2. So if you square a number and the result is even, it means that the original number was also even. Make sense? If you're not sure, let me know so I can explain it further. Okay, makes sense.
Go
Good.
ahead.
Right. Go again, you say? Or say go ahead, which
Yes.
one?
Go again.
Go again. So I'm saying that I'm right on the board. I didn't want to write it off to mark it out, But let me say it. If x squared is even, let's say x was a number. If x squared is even, then x must have been even. See if that makes sense to you. If x squared is even, if x is an integer, and the square of x is even, it means that x itself must have been even. So if x is an integer, and the square of it is even, it means that x was even.
Okay, sir.
So what I'm saying, all right, so you understand what I'm saying, but do you see why that is so? Or you need to be shown why that is so? All right, a matter of fact, make it easier for you. Can you find the square of any number that is even, that was not even before you square it? If you can do that, then I can give you some money. How much you want?
Repeat it again, sir.
So, can you find a number whose square is even, but the original number was not even?
Yeah.
That is, the number was an integer, no?
Huh?
The number was an integer. Remember we said that a and b are integers.
You can find a number that's odd when you square it to get an
Let's,
even number.
I can't put it that way then.
No, sir.
So it's an integer. No, not possible. So that means that if the square is even, that means that the integer itself was even as well before you square it. That's what we're saying. Because we assume that a and b are integers. Remember that for a rational number, a and b have to be integers. So if the square is even, then it means that it wasn't even before you squared it as well. That's what we are saying. Make sense now? Clear on that? Since I can't think of any. In other words, the number was either odd or even. If you square it and it's even, it was even before you square it. That's what we're saying.
Yes, sir. Got that. It must be even.
All right, must have been even before. So we're saying that if b is even, then 5b squared is even, which means that a squared is also even, which means that a was even. So this implies that A is even as well. But what? Oh crap. Even. But we assumed that A over B was in its simplest form. And if B is even and A is even, then A over B would that have been its simplest form then? If both of them are even. If B is even and A is even, would A over B have been in its simplest form?
Should.
I didn't hear that.
Yes, sir. They should be in their simplest form.
Well, I don't think I understand the question. Let me repeat the question a different way. I'm saying that if B is an even number and A is an even number, would A over B have been a fraction in its simplest form?
No, sir. Because
Why not?
because if they're both even, then one of them should be 1 in order for it to be in its simplest form.
That's true.
You're saying the right thing, but you make a mistake when you say one of them should be 1. It's not one of them should be 1. Something for the both of them should be 1.
The denominator.
Not necessarily the denominator. None of the numbers have to be 1, you know. No, the numerator nor the denominator have to be 1. Something has to be 1. It's a F word.
What?
The F of both of them have to be even. I mean, it has to be 1. Pardon. Should I say the F?
Should I say the right word?
I think I said that wrong. It's a word can be used, but if I give it out, if I say something more, you give it away. It's an abbreviation. Something of both of them has to be 1.
The coefficient? Well, that makes sense.
Coefficient. It's a three word.
Factor.
The last word starts with F. What?
It can be factor.
Yes, man, that is it. For it to be in the simplest form, the highest common factor of both of them has to be 1.
Oh, highest common
Couldn't
factor.
have been 2. See, that makes sense to you. For a fraction to be in its simplest form, the greatest common factor of both of them has to be 1. For example, 2 over 3 is in its simplest form. Why? Because the greatest common factor for both 2 and 3 is 1. 5 over 7 is in its simplest form. 6 over 7. 8 over 9. All those are in the simplest form because the greatest common factor for both numbers, numerator and denominator, is 1. 4 over 6 is not in its simplest form because the greatest common factor of 4 and 6 is 2, which would be the case if both A and B is even. So, the square root of 5 being equal to A over B would mean that A and B both cannot be even. Because if one of them is even, then the next one has to be even as well. That's what we're saying right here. So we have now come to the conclusion that B is not even, A is not even. So A and B can't be even numbers. That's why we went through this a while ago. So we say if B is even, then A is even. And if A and B are both even, then A over B would not be in its simplest form. So we can't use that. It's a contradiction to say that A over B was in simplest form. So far we have now shown that both A and B not even. And why? Because I can't write everything, so if you're writing it, you can write before that. If B is even, 5B squared is even, which implies that A squared is even, which implies that A is even. And since A over B was in its simplest form, B nor A can be even, because then A over B would not have been in its simplest form, because it would have led to a contradiction. Okay with that? Okay, so writing.
Yes, sir.
All right. So we then have to go to B is odd. Now, if B is odd, then here's what's going to happen. Okay, I'm going to need more space for this. So if b is odd, then we're going to have to do some. So let me know if you finish writing everything. I'm going to have to do some erasing. Or I can probably just squeeze it in here in the meantime. So if b is odd, then b squared is odd as well. And if b squared is odd, you see that we're multiplying b squared and 5, both odd numbers, which would mean that a squared is odd. All right. So how do you normally write an odd number? Oops, what's a normal way to write an odd number? The general way of writing an odd number, using like x or n or whatever. Like an even number is 2 times x. Saying that if x is an integer, an even number is 2x. How you write an odd number?
Like n plus 1.
N plus 1, all right. Say that again?
You're right. 2n plus 1.
Oh, okay. I wasn't sure if I heard the 2, that's why I have to repeat it.
I didn't
Let
say it.
b.
I didn't say the 2.
Oh, okay. Because you know that a 2n will make it even, but then if you add a 1, remember we're using n as an integer. So any odd number can be expressed as 2 times an integer plus 1. Every odd number in the world. So we're going to let b equal to n plus 1. All right, I definitely need to erase now. Remember that we're going to be going from right here, from using this. I'm going to circle it. This thing right here. So if b is odd, then b squared is odd, which means that a squared is odd. So we're going to let b equal to n plus 1, and we can let a be equal to 2c plus 1. So both n and c are integers. All right. So let me know if when you finish writing, then we can finish this proof. The other proof is shorter, but this one you can see everything clearly. So far we have seen that b and a cannot be odd, cannot be even, because one of them is even, the next one must be even as well. And that would lead to a contradiction because a over b, what is the simplest form? So we're going to try the odd method and see what happens. Anyone still writing? Or is anyone writing? That's a better question. You're not writing, Lafleur not writing, Anthony not writing. Okay, let's clear the board. So we have so far b equal to n plus 1, a equal to c plus 1. So we're resuming from right here. 5b squared is equal to a squared. And b, we have let b 2, hold on, what did I say? I think I said 2n. 2n plus 1. Remember, n is an integer, and c is also an integer. So we have 2c plus 1 right here. Now, if we expand this, we're getting 5 times 4n squared plus 4n plus 1 equals to 4c squared plus 4c plus 1. Expand this, we have 20n squared, 20n 5 over here. And by the way, this works for any integer that doesn't have a square root. You can try with it to see it works out. Let's subtract 1 from both sides. That gives us 20n squared plus 20n plus 4. Over here we have 4c squared plus 4c. All right, looking good. Now, as you can see, you can factor out 4, but that would not really be helpful for us. Well, it could be. But let's factor out 2. Okay, let's divide both sides by 4. Divide both sides by 4, you get that. No. Let's divide 4, take out 2, take out 1. What's the best way to do it here? All right. I want to get 2. Yeah, so divide both sides by 2. So we get 10n squared plus 10n plus 2 is equal to 2c squared plus 2c. All right. Good. So on the left side, we have 10n squared plus 10n plus 2. Right side 2c squared plus 2c. Now on the right side, if you factor out the 2 over here, you're going to be left with 2 times c squared plus c. Remember that we said that c is an integer. So on the left side, we can clearly see that we have an even number. Okay, but on the right side, we have an even number too. What's going on here? If we were to factor out 2, well, that's even too. Wait, did I make a mistake before? Let's see. Oh. Oops. Wait, sorry. I made a mistake in the third step. Let me clear that. Sorry about that. So remember we said that b is 2c plus 1? Or I think we said 2n. And a is 2c plus 1. Alright, so expand this. I think 2n times 2n, that's 4n squared. 2 times both of them is 4n. And the last one is 1. Over here, we have 4c squared, 4c, and 1. Expanding this by 5, we're getting 20n squared. Four C. Okay. Right, subtract the 1 now. Okay, do I have to subtract the 1? On the right, we have an odd number. On the left, can I prove that that number is odd or even? Factor the 5 from here leaves it even. Well, this is most interesting.
But if you subtract
I
one,
want
then
to show subtract the 1, yes, but if I subtract the 1, I'm going to get an even number on the right. What is happening is I'm getting an even number on the left as well. I don't want that to happen. Let me see. Maybe I'm missing something. I randomly pick 5, but it seems as if this thing doesn't work with 5 so well. Alright, let's we have 4c.
you can divide
On
by
the
4.
left, if we divide by 4,
Zero.
problem that's going to happen is on the left side. On the right side, you're going to get c squared plus c, which You're right, you know. Divide by 4 can work because it can carry over the 1. Alright, yes, let's do that. Divide both sides by 4. That gives us, I don't know if you divide by 4, get a 5. I don't want 5. Oops. No, divide by 4. What I should have done was divide both sides by 2 initially. No, it couldn't work. Divide by 2, we had the 4 right there. I'm going to try what I was thinking a while ago. I'm going to divide by the 4 as I mentioned. We'll give 5 over here, give 1 over there. Well, I'll give 5 over here, 5s. Over there, we're going to get c squared, which is 1. It doesn't work as well. But let me see. Maybe it works out. Divided by 5, we're getting, no, can't divide by 5. Factor out the 4. We're getting 4 times 5n squared plus 5n plus 1. Over here, we're getting c squared plus 1 plus c, which means that both numbers are even.
But then, sir,
Yeah.
if you divide both sides by 4, wouldn't you have one that is
If you divide both sides by 4, you're getting this. Which you can't show is even or odd.
you're trying to show that both sides should be odd?
Both sides should be what?
What you're trying to do, show that both sides?
No. No, we're trying to show that one number is odd, one number is even.
One side is odd and one side is even.
Right.
But sir,
But I'm not seeing how that's possible.
but if you take the 1 over the other side, it'll be minus 1.
But that's how we needed to. That's how we needed the 2. I randomly pick 5, you know. I should have stuck with what I know. I know it works for 3. I just assumed it would have worked for 5. I didn't try it.
Why it's not working for why does it? Why would it work for one and not for the other?
Well, the other proof would work for this, you know. There are 2 methods to prove it for 3. I know that one of them works for 5 no matter what. Well, there's one method that works no matter what all the time. That other method only works for 3. Oh, hello, Jeremy. So I am going to do what I'm sure of, and I'm going to check the other method to see if it works for 5 as well.
Okay, sir.
On my own time. I won't do it in the class. But I know it will work. But just because I thought this would work as well, so let me work what I'm sure of with the 3. Okay. So my apologies. This method doesn't work for 5. There's no way I can show that one side is odd, one side is even. It's not working out. Well, no, I can't. Maybe it can work, but I'm not envisioning how. If I divided out the 5 here, you get 1. No, it doesn't work. You get 4. 4 plus 4 plus 1. Over there we'd have. Oh. Over there you couldn't divide by 5. No, sir. I'm not seeing it. So much for that experiment. Let me do it for 3. My apologies. So since Jeremy just came just in time to catch this. Show that the square root of 3 is irrational. I'm going to do that method for 5, you know. You know what I'm going to do it. I won't do it. I think it doesn't work. So I'm going to show that the square root of 3 is irrational. Show that the square root of 3 is irrational. I'm going to use the same method a while ago. So I must always check things before you come to class. You know. I've never done it before, but this has never happened before either, so it won't happen again. So show that the square root of 3 is irrational. So the same process we did before. We're going to assume a contradiction. We're going to assume that the square root of 3 is rational. Assume root 3 is rational. So this will just cement in your brain what we did before. So if the square root of 3 is rational, it means that we can write the square root of 3 as an integer over another integer, where b is not equal to 0. So we can, whenever a number is rational, we can express it as an integer over another integer. That's what rational means. But of course, the one in the denominator can't be 0. One at the top can be 0, but the one in the denominator can't be 0, or it would not be a number at all. It wouldn't be a real number. So we are going to assume that a over b, root 3 is rational, so we can write it as a simplified fraction a over b. Simplified doesn't mean that a and b have no factors in common except 1. So the highest common factor of a and b is 1. So once a fraction is written in its simplest form, the highest common factor of a and b is 1. Don't have any other common factors, but common positive factors. Because negative 1 can go into both of them as well. All right, so that's our assumption. Root 3 is rational, which is a over b. Now, having done that, we can now square both sides to give us 3 squared is equal to a squared over b squared. B squared. We multiply both sides by b squared, so we're getting 3. Sorry, I made a mistake here. This is 3, not 3 squared. The square root 3, we get 3. So 3 times b squared is equal to a squared. Now, having gotten to this stage, we can now show that b can't be an even number, a can be an even number. So we can start by saying if b is odd, is even, beg pardon, if b is even, then 3b squared is even. Oh, come on here. Then 3b squared is even as well. Why is that so? Because if you have an even number and you square it, that result even, and multiply that number by any number, any integer, it's still going to be even, including 0. Don't forget 0 is even, you know. So if a number is even, in this case b, then its square is also even, and any integer you multiply by, in this case 3, will still make it even.
Sir said if, that is what, if 1 is even, then?
B.
Oh, look like 1, sir.
Yeah, that's why I make sure to talk when I'm writing. So if b is even, then 3b squared is also even, which implies that a squared is even. And if a squared is even, what does that say about a? Oh, what's wrong with my writing? Anybody? We discussed this before.
It's gonna be
If
even.
a squared is even. Come again?
Even.
What is even?
If a squared is even, that means 3b squared is even.
No, we did 3b squared already. We said that if b is even, then 3b squared is even, which means that a squared is even, which means that what is even?
A.
A. Correct. If the square of an integer is even, it means that the integer was even. So we have shown that if one of them is even, then the other is even as well. You could start with a if you wanted. If a is even, then a squared is even, which implies that b squared would have been even, which meant that the b was an even number. Because of course the 3 is not even, so the other number must have been even. Now this premise goes from, remember, both of them are integers, you know. A and b are integers. So if the square of an integer is even, then the integer must have been even. You can check it if you want. It has to be even. It's impossible to square a number. Let me say it a different way. Sorry. It's impossible to square an integer and get an even number. The integer is not even. It's impossible.
So can you actually prove that though? Or you just have to go by trying some plenty numbers?
I can prove it. It's a proof. It's a theorem, you know. It's just that we have to use that one to do this one. We can prove it. All right. It's a matter of fact, the proof is a contradiction just like this. You would assume that the number was not even, and then go from it like that. So you say something like, okay, let x squared be even. I would say x squared is equal to 2 times something squared, and then you say that the thing can be divided by 2, whatever. But I can show it to you next time if you want. Right. Where was I? So we are saying now that if one of them is even, A or B, then the next one is even. But that would mean that A over B can be expressed as 2 times something over 2 times something else, or the same thing if you want. But this would have meant that A over B was not in its simplest form originally, which we assumed to be this case. So this is what we call a contradiction, because it goes against what you have assumed. We assumed that A over B was in its simplest form. I didn't write on the board this time, I wrote it last time. But I said it though. We assume that A over B is in its simplest form, but now we are saying that if B is even, then A is even, which means that you could have actually cancelled these two things right here to simplify the fraction further. So that's a contradiction. Therefore, B, what is wrong with my therefore? I'm trying to write rid of that. It's not good. Oh, therefore, B is odd. Those are the two possibilities, you know. It's either an even number or an odd number. Why? Because both A and B are integers, and integers are either even or odd. Show that it can't be even, because it led you to get an even number over an even number, which can be simplified further. We assume that it was already in its simplest form, so that's not supposed to happen. So B must have been an odd number. And if B is odd, then B squared is also odd.
What you have there is that therefore B is odd, or that's an equal sign.
Therefore B is odd.
Okay.
Then B squared is odd, which means that A squared is also odd. How come? Because if B squared is odd, you multiply an odd number by an odd number, the result is odd. So therefore the A squared must have been odd as well. So there's no even numbers there. So far we have shown that if root 3 is a rational number, then it means that when you write the fraction, it's an odd number over an odd number. So we have gotten to so far. None of them can be even. None of the integers in the A over B can be even. So we have gotten to so far. So far. We don't know if it's true yet, but so far we know that A and B must be odd. So B is odd, which means that B squared is odd, of course, because B squared is multiplied by 3B squared, and A squared must be odd as well. Sorry, because B squared is multiplied by 3, then the result must be an odd number, which means that the A squared must also be odd. All right. So if B is odd, we can write it like this. Let B be equal to 2 times n plus 1. What do you see first? Whatever, doesn't matter. And A will also be an odd number, which can be expressed as 2c plus 1. You could also use minus 1. When you subtract 1 or add 1 to an even number, the result is odd. Anyway, so far we have B is 2n plus 1, A is 2c plus 1. So we're going to go back to using this little portion right here to finish the proof. That root 3 is irrational, beg pardon. So let me know when you guys have finished writing up to that point. And don't worry, this time it's going to work out using this method. And we'll try the other method with the other one as well. The other method works for everything. I'm pretty sure of it. I didn't try with this one before. Is anyone still writing?
I'm finished, sir.
All right.
I'm not sure if she's finished.
Oh, she's reconnecting, so let's see how quickly she gets back. Catherine, are you hearing me?
Yes, sir.
You finished writing?
Yes, sir.
Good. So coming back to that thing I circled a while ago. So we have the 3b squared, we're going to use that right now, equals to a squared. And we have assumed that b is 2n plus 1, an odd number. So 2n plus 1 squared is equal to 2c plus 1 squared. Expanding the left side, get 4n squared plus 4n plus 1 in the squared bracket. And squaring over here, we get 4c squared plus 4c plus 1. So on the left, we have 12n squared, 12n plus 3. On the right of the same thing. So I'm going to subtract 1 from both sides to leave us with 12n squared plus 12n plus 2. On the right, we have 4c squared plus 4c. Dividing both sides by 2, we have 6n squared plus, what's this? 6n plus 1 equals 2c squared plus 2c. All right. On the left, I'm going to factor out 2 from these two things here, which leaves us with 3n squared plus 3n plus 1. On the right, we just factor 2, so we have c squared plus c. What kind of number is on the right side? Even or odd?
Even.
Even, because remember c is an integer, you know? Because we let a be equal to 2c plus 1. So c is an integer, and the same thing for the b. 2n plus 1, n is an integer. So on the right, we have an even number. What kind of number have on the left? It's a question, you know. What kind of number do we have on the left side? Even or odd?
It's an odd.
A number. I'm sure of that because when you multiply a number by 2, it's even. And once you add 1 to it, as a matter of fact, that's the exact definition we used a while ago, 2n plus 1. So it's 2 times integer plus 1. That must be odd. Over here, we have an odd number because we're multiplying a number by 2 and then we're adding 1. On the right, we have an even number. But that's an even bigger contradiction that we had before. We're saying that an even number is equal to an odd number. It is impossible. So it means that b could not have been odd and b could not have been even. So if b is not an odd number and b is not an even number, the same goes for a. A is not even, a is not odd. Then it means that it was impossible to express root of 3 as a over b as an integer of an integer because a is not even, a is not odd. And the same goes for b. So if b is neither even or odd, because it leads to this madness down here, getting odd number equal even number, and because before we showed that it was not in its simplest form, then we have contradiction both ways. It's not even, it's not odd, therefore root 3 cannot be expressed as a over b, two integers. So root 3, go ahead.
So the idea is, even though with some numbers may work, for example, when we use 5, we show that we have both sides being equal, as in being odd, equal odd, or even equal even. As long as you can find something that doesn't work, it doesn't work overall.
Yeah, it doesn't work overall. For the 5, I'm going to show you the other way. Remember I said I'm going to show you 2 methods. This is one. The next method I know will work for 5. All right, let me not say no. I am very confident it will work for 5. Try to start with that for the 5. Anyway, but take this off. I'm going to show you the other method after this. I like this method because it's more straightforward. That's why I was trying to use it for the 5. But I'm not seeing how it would work. We have to stick to the other one. The other one is a little more intuitive. This one is straightforward.
Sorry, I don't understand.
Which part?
How is it not irrational? How is it irrational?
Because you could not have expressed you could not have expressed the root of 3 as an even number over an odd number, or an odd number over an even number, or an even over even, or odd over odd. You could not have been expressed like that. Remember, when you're expressing a rational number, you should be able to express it as one integer over another integer. And because we were unable to express it as integer over integer, either odd over even, or even over odd, or even over even, or odd over odd, I said already, then it means that you could not express it as a rational number. Because b could not have been even, and b could not have been odd. So because b is not even and b is not odd, it's not rational.
So therefore, the definition that any number that can be written as a fraction is a rational number is wrong. Because I'm assuming that you can write root 3 as root 3 over 1. Wouldn't you say that is a fraction? Or a fraction is defined similar to that as a over b?
You know, it's a good question. I don't know what the actual definition of a fraction is. Look it up. That's a good question, you know. I know how to define a rational number, but I don't know what the definition for a fraction. Fraction definition. Oh, but this doesn't make sense either. Because this one is saying a numerical quantity that is not a whole number. That's not true.
Yeah,
One is not a whole number. It's not a fraction. Well, you can write it as a fraction. Like 7 is a whole number, but it's also a fraction. Well, maybe not. It's rational. It's not a fraction. I don't know what a fraction is. That's a good question. I don't know what a fraction is.
Interesting. Okay.
I guess
the definition for a fraction will come in the lower level of mathematics.
Yeah, this is part of a whole.
It might not be accurate.
Right. I'm not finding any fancy definition online. That is a good question, though. Oh, here someone says a fraction is a numeral that represents a rational number. That's a very good question, Anthony. So I'm going to research what a fraction is. I know what a rational number is. I don't know what a fraction is. I've been so used to using it, but not actually knowing what it means. By the way, Michaela, did you understand what I said a while ago about the even and odd? Michaela.
Sir?
Do you understand what I said about even and odd?
No, sir.
We know why you never say something. All right, look here. You see a while ago we showed that the b could not have been even. You got that part? Yeah.
What? No.
Remember, we first part before we got to this. Hello? I said what?
At the end, you have odd under the 3b squared and even under a squared.
Yeah. What is the part you don't understand?
Yes.
Oh, good. So on the left side, look here. On the left side, we see 2 times an integer plus 1. It results in an odd number. Because an integer by definition, an odd number by definition is 2 times an integer plus 1. On the right side, we have 2 times an integer. C squared plus C is an integer. Multiply by 2, we get an even number. So we have shown that if b is an odd number, you're going to be getting an odd number equal to an even number, which is a contradiction. Nothing that is impossible. That cannot happen. An odd number cannot be an even number. So because an odd number can be an even number, the premise of all of this was that b is odd. So before we showed that b could not have been even because it resulted in both a and b being even. which could not have happened because A and B, A over B was already in its simplest form. So it could not have been an even number over an even number. It's a contradiction. Contradiction means it goes against what we assume to be true. And then we came here now to show that if we say B is an odd number instead, you get another contradiction, which is saying odd equal even. Odd cannot be equal to even. So it goes against the next thing we assumed. We assume that B is either going to be even, and B is either going to be odd. B is either going to be even or B is going to be odd. And since B can be even and B can be odd, it means that the other assumption we made was untrue, which was the first assumption that root 3 is irrational. So whenever you're doing a contradiction, a proof by contradiction, you assume certain things as they go along. And if each of them are not working out, it means that the original assumption was wrong. So we assume that, let me show you the breakdown. We assume that root 3 was rational, which means you can express root 3 as a simplified fraction, A over B right here. And A and B must be integers. From that proof, from that assumption, we say, okay, let's check what happens if B is even. Remember, for it to be integer, it's either odd or even. We check what happens when it's even. We got foolishness, contradiction. So we check what happens when it's odd. More foolishness, odd equal even. So therefore, B is not even, B is not odd. That means that root 3 was not rational. Because everything that stemmed from assumption that is rational led to contradictions or impossibilities.
So, sir, because odd equal even, odd cannot be equal to even. That's why it can't be rational. It's irrational.
That's part of the reason it can't be rational.
That's why it can't work.
That's right. That's why the assumption that
So,
it's rational
sir,
could not work.
what it have to equal to work?
But it have to be equal to work. It means that both of them will either have to be, you should be able to express both of them as an odd number, both of them as an even number. Or both of them as odd or even. But we could not have expressed them as even, we could not have expressed them as odd. We could not have expressed one as even and one as odd. Matter of fact, all we did was just check if B is even or B is odd, and both of them led to foolishness. Because B is not even, B is not odd, that number down there is not rational. So because one of them is not rational, the whole thing is just irrational. Make sense? Look here, I'm sure something. If you say that a number is rational, you can express it as x over y. It means that y is either going to be, let's focus on the y, that's the y. It means that this number down here is either an odd number or an even number. If you try to prove it and you can't prove that, when you try the number to be odd, you get rubbish. If you try the number to be even, you get rubbish. It means that the number is not even, the number is not odd. Therefore, it cannot be expressed as a rational number. Because the only way a number can be expressed as a rational number is if the denominator is odd or even. That's what the definition of an integer is. An integer is either odd or even. If the integer can be shown as odd and the integer can be shown as even, it's not an integer. Which meant that the whole premise that the thing was rational is untrue. It must have been irrational. Make a little more sense now? Yeah.
I'm not sure, sir.
Not sure. Anthony, you understand it? Maybe sometime when peers explain it, it's better now. Try to explain it in different ways, but you're not getting it.
I think, I'm not sure. I think maybe.
Or you don't understand it?
Understand it. No. I understand.
Okay.
Probably if you take it from the top, she'll get it. Basically,
Stop trying now.
I know. Okay, so you're basically trying to show that the square root of 3 is not a rational number. And a rational number, because we know that a rational number can be expressed as an integer over an integer, where the denominator is not 0. So now what you did was basically set up an original equation where you say, okay, all right, let's look at B and A. If you take the denominator, which is an rational, well, you did several things, right? This last part here, what you're doing is showing that it cannot be
Odd.
odd, right? Cannot be odd. Both of them cannot be odd, right? You showed basically that
No, well, I show that the
A
B
and B are
cannot be
both.
odd.
B cannot be odd, true.
I focus on the B.
Okay, so you're showing that B cannot be odd in this step. Okay, all right. So when you square it, but you also wait for A. When we have 2C plus 1, isn't that showing that A is also an odd number?
Yeah, because we had said that we had shown that if B is an odd number, then A must have been an odd number as well.
Okay. Okay.
So that's why we wrote it as an odd number as well. Because what happens, is if B was even, then A had to be even. Because remember, 3B squared was equal to A squared.
Right.
I also show that if B is odd, then A had to be odd as well.
Right. So when you were showing that both if B is even, then when you showed that if B is even,
yeah, then A must have been even.
A must be even. All right.
Which meant that A over B was not in simplest form,
right.
which we assume to be true.
Right. So in this case, now you're basically you're showing that if B is odd, then A must be odd as well too. But when you work that out, you did not get that.
Right.
So that's basically yeah. You're saying
so,
that if B is odd, then A must be odd as well.
Right. Right. So Michaela, what we assume, just put in a synopsis one more time. We assume that A over B, root 3 is equal to, listen very carefully now, root 3 is equal to an integer over an integer. That's what a rational number is. We assume that. So we show that, okay, if root 3 is equal to A over B, both integers, then that means that integers are either going to be odd or even. Which, okay, either odd or even. Check what happens when it's even. It leads us to something that was not true. Check what happens when it's odd. It leads us to something that was not true again. See, it led us to something right here at the end, saying that the odd number is equal to an even number. So in both instances, when you check if the integers are odd or even, we got contradictions to what we assume to be true. So it meant that what we assumed to be true was not true. The assumption was incorrect. And if the assumption was incorrect, it must be the other thing that is true. Because numbers are either irrational or rational. We assume that if it was rational, we got contradictions all over the place. So it must have been irrational instead. I'm trying to put it in a nutshell, Michaela. Does that make more sense now?
I think I get it now.
All right, okay. Just look it over when you finish and see if you can catch it. Because I want to show you the other method now, quickly. And this method I think would work for root 5. Not I think, it will work for root 5. Oh, is anyone writing? After all that talking, it must be finished. Let me just erase this. The other method is same thing again. We assume that root 3 is irrational. We assume that root 3 is rational, which means that root 3 can be expressed as A over B. Square both sides again. If I can just jump a step, I'm going to get 3B squared. I don't have to rush. 10. There's only one question. 4 classes, more, both 3 of them. Anyway, so 3B squared is equal to A squared. Square both sides, multiply across. Get that. Now, so this is where it gets a little more technical. Before I go any further, I'm just asking something. Think about this carefully now. Remember, A and B are integers. A and B are integers. So if you square an integer, means that whatever number could have divided it before, and divide it 2 times now. See if that makes sense to you. Let's say x is equal to m times n. So x is equal to integer times integer. Remember, all of them are integers. So if you square x, it means you're going to be squaring mn. So it's mn times mn. Meaning, whatever number could have divided the x before, you now divide it even twice as many times. Put it that way. So if you could have divided it before, like say 4 could have divided the x, it means that 4 can divide it 2 times now. At least 2 times, I should say. Because maybe we could have divided it more than 2 before. So whenever you square a number, it means that if a number can divide square, then it can also divide. Let me rephrase that. If you square an integer, it means that if an integer could have divided it before, the square, then it can also divide the square root. So in other words, if I tell you that 10, not 10, use a letter. If I tell you that x squared can be divided by, say, 7, oh, prime, I should say prime. If an integer if a square can be divided by a prime number, it means that the what call it? The prime number can also divide a number that is not squared. That's what I was saying. If a prime number can divide the square of an integer, then the prime number can also divide the integer. Is that something that you guys knew or didn't know? All right, let me ask a different way. Did anyone not know this? Oh, beautiful.
New to me, sir.
New to you. All right, well, you know it now. So if an integer if a prime number can divide a square of an integer, it means that the prime number can divide the integer. And once again, you can, well, you weren't here earlier, but since you're here now, if you can find something to disprove this, I will give you, how much money you have? What next step? Give you $5,000, 10,000, 22. Matter of fact, if you can prove this to be untrue, then you can win a Nobel Prize. It's actually an accepted proof in math. I shouldn't have told you that. Should make a good try. So anyway, once a prime number can divide a square, then the prime number can also divide. Sorry, once a prime number can divide a square of an integer, the prime number can also divide an integer. Anyway, that's what we're doing. Do this quickly, rub it out. Get started. So as I was saying, we're going to express the root 3 as a over b. Simplest form again. That means that b squared times 3 is equal to a squared. Right. So what this means is that if 3 times b squared is equal to a squared, it means that a squared is divisible by what? What are we sure can divide a squared? What number are we sure can divide a squared without a remainder? Come on, it's right there. Look at it.
2.
By 2.
Sir, B.
Well, yes, b. But I said, what number are we sure can divide it without a remainder? Number. Real number, no.
Sir, 3.
3. Look at it. It's 3 times the integer equal a squared. That means that 3 can go into a squared without a remainder. It's right there, no. If I tell you 2 times x equal y, that means that 2 can go into y without a remainder. That gives you x. Anyway, it's right there on the board. 3 can go into a squared because 3 times, remember a and b are integers, you know. So if you divide a squared by 3, then it means that, sorry, if you divide a squared by 3 right here, you're getting b squared. Okay, just cross or transpose a squared over 3 is equal to b squared. That's what it's saying. Anyway, so a squared is divisible by 3. Or I should just write in 3 is a factor of a squared. Remember the proof I just told you about a while ago, the theorem I told you? If a number, if the square of an integer can be divided by a prime number, It means that the prime number also divides the integer itself. So since a squared is divisible by 3, it means that a, which implies, therefore, a is divisible by 3. It's simple. By 3. What does this mean then? If a is divisible by 3, what does that mean? What does that mean for b? So far I've been asking you guys questions and I have to answer them. So think about it. What does that mean for b? A squared is divisible by 3, which means that, let me not waste time. That means that a is written like this, 3 times some integer. Because remember, a is divisible by 3. If a is divisible by 3, it means that we can write a as 3 times some integer. Because 3 is a factor of a. Which means that, let's go back to, well, I was going back to what we used. We're using this right here. So since 3b squared is equal to a squared, then 3b squared would be equal to 3c squared. That's a. So we just show that a is divisible by 3. Which means that 3b squared is equal to 9c squared. Let's square 3c, get 9c squared. Divide both sides by 3, and we're getting b squared is equal to 3c squared. C is an integer. But we'll look at this. It means that, what does that mean for b? If b squared is equal to 3c squared, what does that tell us about b? Let me make it even more. If bc squared is equal to, if b squared is equal to 3c squared, what does that tell us about b?
It's divisible by 3.
Correct. Therefore, b squared, and by extension b, is divisible by 3. Divisible by 3. So hold on there. B is divisible by 3. C is divisible. B is divisible by 3 and A is divisible by 3. What would you assume? What did we say about A over B from the beginning? What did we say about A over B right from the start?
They must be integers.
Right. What else? What about the whole fraction? What about A over B? What did we say about it? It was in its come on, people. Not paying attention, man.
Form.
Simplest form, thank you. And if a fraction is in its simplest form, what is the greatest common factor?
1.
But we have just shown that A is divisible by 3 and B is divisible by 3, which means that we have a factor bigger than 1. In other words, A over B can now be written as 3 times something over 3 times something, which means that you could have simplified it further by 3. This is a contradiction to what we assumed earlier. We assumed that we could have written root 3 in its simplest form as A over B. We have now shown that if that assumption is made, you can find an even bigger factor than 1, which would mean that A over B was not in its simplest form, because now we can write it as 3 times an integer over 3 times an integer, which is a contradiction. This happens whenever you're trying to write square root of a rational number, square root of a prime number, and it's as a rational number. Whenever you try to do that, you encounter contradictions like this, which meant that A over B was not in its simplest form, as we assumed before, and therefore it contradicts what we assumed. As we assumed that root 3 can be written as a rational number in its simplest form, which leads to a contradiction. which meant that our assumption was incorrect, and our assumption was it is a rational number. So the assumption was incorrect, which means that root 3 is irrational. Yes, Anthony?
Did you say that this happens when you're trying to find the square root of a prime number?
No matter the square root of any number that's not a perfect square. You can check with the square root of 6 as well. Square root of any number. So I said this one works for all of them. But that one that I did before apparently didn't work for 5. I'm going to see if it works for 7. That would be interesting. Yeah, I've tried it for at least 4 different numbers before, and then I tried 5. Just said, okay, let's try 5 today in class. You know, didn't work at all. Anyway, so this is a contradiction as well. Therefore, root 3 is irrational. All right, let me stop the recording right here.